All right, our next lesson, 8.2, is all about vectors in the coordinate plane, and we're going to discuss finding magnitude of resulting vectors that really don't have any application. So we're going to be using a formula. We're going to talk about scalars multiplied into vectors, vector addition. What else is in here? Oh, unit vectors. We got lots of good stuff coming up here. So I would suggest, if you have it handy, to make sure you have a calculator, of course, your worksheet 3, and we're going to do a little bit of unit circle work today as well. So if you have it memorized, that's awesome, but if not, that's okay too. We'll just show you what it looks like again. It's been a while. So when we have a vector in component form, they use a lot of vocab here on this page, but none of this is really new to us. The magnitude and direction of your vector, we're supposed to draw them like by scale, but we never do because we're lazy. Although I probably should. My pictures are so ugly. So to find down here, there's some stuff underlined. All these vectors are equivalent because you can move the vectors around in the coordinate plane. But to find the component form of the vector that is not in standard position, you can use the coordinates of the initial and the terminal point. So this time we don't really have application questions. We just have kind of what looks like ordered pairs, but it's the initial and terminal position of the vector. So this is going to look really familiar because it really just looks like distance formula, doesn't it? Which is pretty much what you're doing. The resulting vector you can find by taking x2 minus x1 for the horizontal components, and then y2 minus y1 for the vertical components. But be careful, because the initial point is x1, y1, and then the terminal point, or the end of the vector, or the second vector, is x2, y2. So make sure it goes in that order when you're finding it. So this notation means from A to B, which is what the arrow indicates. So finding my resulting vector's components, I look at the x's, but I remember I'm finding the distance from x2 minus x1. So 3 minus negative 4 would be a 7. And then negative 5 minus 2 is negative 7. I don't know why I switched colors, but I did. All right. So that's the component form of the new resulting vector AB. So then they want to know, well, can you find the magnitude? Well, that's essentially just a Pythagorean theorem or a distance formula question, because that's what we're finding. So that's why it looks so much like distance formula. But remember that x2 minus x2 minus x1, that's just the length of this vector. So if you know the length of that vector and call it A, you're good to go. Same thing here. This is vector B, length B. So it's the square root of A squared plus B squared. I love how math just keeps repeating itself, like you're going to forget what distance formula is all of a sudden. We like to relate things that are new in math, not that this is new to anybody, but to things that we already know. Makes things more understandable. So here they give us the two vectors, and the resulting vector is x to y. So they found the new resulting vector to be negative 6, 5. So, and they found their components here right here. These are the original vectors, here and here. I can read. So the magnitude would be the square root of negative 6 squared is 36 plus 25, which is 56 squared is 61, which is a good answer. For some of the work we're going to do today, an approximation for the square root of 61 is 7.8. So it depends on what your purpose is. If they want an exact answer, because you're going to do more work with the exact answer, keep it as the square root of 61, or if it's reducible, please do. So here, they want component form of the new resulting vector and the magnitude. So this should not be too bad. Vector from A to B, remember that's our notation for vectors, is going to result in the new vector. Let's see, it's got to go x2 to x1, so that's a 40. And then y2, okay, negative 8. Man, I should be able to subtract by now. So then our magnitude is just simply, I say simply, but I don't really know what this is, so hopefully I already typed it. And I'm just going to write 8 squared because the negative is going to be negligible in the moment. This comes out to square root of 845, which probably reduces, I don't know. And it comes out to 29.1 for an approximate magnitude. All right, number 2, same stuff, guys. This is pretty boring, actually. Oh, no, that's not even, I read the wrong answer. This is 40.8. Hello. This one comes out to 29.1. Let's figure out how. So A to B is 7 minus negative 15 is 22. Negative 19 minus 0 is negative 19. So my magnitude, which they use the notation absolute value of v, the distance of the new vector. That's what that means. If you want to think of it that way. It's not exactly what it means, but I like that. I keep calling it magnitude because that's what we have been calling it. Is the square root of 22 squared plus 19 squared. And this one, oh, see, that wasn't right either. Gosh, Bruzo, this is 1664. Learn to read, girl. This is square root of 845, which is approximately 29.1. There we go. All right, so sorry for rattling off the wrong answers. I'm going to skip 3 because that's pretty boring. Okay, vector addition. You add the parts together. It's not rocket science, is it? Now, vector subtraction, you have to be careful because you're adding like negative b, so it has to go in that order, so just be careful. And then scalar multiplication works exactly how you think it would. It just multiplies everything by that scale factor. So, just for fun, let's go ahead and add s plus t. So here's s, and here's t. And if I were to add them together, I would get 4 plus negative 1, which is 3. 2 plus 3 is 5. That really wasn't too bad at all. This one is kind of already done for you. That's a bummer. But 3 times s, they went ahead and calculated by multiplying s by a factor of 3, and they got this new one. They didn't do anything to vector t, but they did add these results together, and they got 11, 9. Probably without any instruction. You would have guessed that was the right answer anyways. Alright, so here we have f, g, and h to do our own work with. So this time they want f minus g. So I'm too easy to mess up on problems, so what I usually do is I write it out like this. What's g? 24, 21. Now, don't worry about, like, sometimes kids get this confused with finding the resultant vector from the first thing we did in the notes. This is different, so we're finding a resulting vector from subtracting the vectors. So 4 minus 24 is negative 20. 2 minus 21 is negative 23. And then this one, I have vector g, which is 24, 21, minus, now instead of 2 times f, like separately, I'm going to go ahead and just double f. So that gives us 8, negative 4. And then similarly here with the plus 3h, instead of writing 3 times h separately, I'm just going to multiply that by 3. So I have negative 3, negative 9. And then I just do what it says. So 24 minus 8 plus negative 3. 24 minus 11 is 13. Yeah. And then 21. Careful, you're subtracting negative 4. So keep that in mind. So that's plus 4. So 25 minus 9 is 16. Yeah. Alright. So there's my resulting vector. Okay, unit vectors. If your vector has a magnitude of 1, that's called a unit vector, and that kind of has shades of unit circle in it, right? Because the radius in a unit circle was 1. So in this case, we're going to take our existing vector and we're going to divide all the components by the actual size of the magnitude of the vector, and then that's going to cut all the components so that way we have unit vectors, which they're going to call u. The horizontal component, when it's written as a unit vector, can be denoted with an I. Don't confuse that I with imaginary I. They're different I's. Imaginary I, when they type it, is like italic and kind of like it's slanty and cursive looking almost. This I is just a regular old second grade lowercase I. Alright, and then J is the vertical component. Alright, let's see this in action. This formula looks really scary, right? Well, all you're doing is you're taking the vector and you're dividing each component by the magnitude of the vector. So, if this is your vector, the first thing you do is you find the magnitude by using this formula. So, they found the magnitude to be the square root of 13, and then they just take each one of these components and they divide them by the square root of 13. But, you know, being pre-calc, we're not happy with an answer that's not rationalized, so then their final step is to do that and rationalize everything. Because why not, you know? This notation will come up next, so hang on for a minute. So here's our original vector. I guess we're going to discuss it right now. They want me to find a unit vector, and then we'll talk about this notation after that. I think. I don't know where I am in my notes anymore. Let's go ahead and find the magnitude. Ignore the I and j thing for a moment. So the magnitude, or you can call it the absolute value of v, is the square root of, let's see, negative 4 squared. So 16 plus 1, which is the square root of 17. Leave it as a radical because we're going to want pretty answers here. So then if I take your original vector and I divide each of them by the square root of 17, I start off with negative 4 over the square root of 17, comma, negative 1 over the square root of 17. But no one likes that answer, right? They're going to want you to rationalize it. So rationalized answer, negative 4 square roots of 17 over 17, and negative 1 square roots of 17, so negative square root of 17 over 17. I kind of skipped the rationalization work because you guys are so good at that right now. This notation, though, this negative 4i plus minus 1j, is a way that you could notate a vector that is written in unit vector form. We'll come to that in a second. All right. Like right here? Oh no, these are just more examples. They are on your notes. You have to kind of scribble, go down to skip over the I and j thing for a moment. We'll come back to that. All right, find a unit vector. Got it. All right, so the magnitude is 16 plus 9 square rooted, which is nice. That comes out to 5. So the unit vector, which they want you to call u, is 4 over 5, comma, negative 3 over 5. So sometimes they're nice and easy like that, where you don't have to rationalize at all. And sometimes they're not. So the, let's see. Oh, you know, I'm silly. These are not. There you go. P. W. I don't care about your notation as much, guys. Clearly I'm not using the right notation either. Alright, square root of 10 squared plus 25 squared. There we go. So this magnitude is, and you want to leave it in radical form and reduced. So I think it comes out to 725 at first. And then after I break that down, that's 25 times 29. So we're going to be using 5 square roots of 29, and this one's going to get kind of messy. So if I divide each of these by 5 square roots of 25, my unit vector is going to need a little bit of work because I'm going to have to simplify a bunch. So what do we have here? We have 10 divided by 5 square roots of 29, comma, 25 divided by 5 square roots of 29. So I'm going to reduce this 10 and 5 and this 25 and 5. So like this is a 2 and this is a 5 now. And while I'm at it, I'm going to also remember to rationalize. So after I hit top and bottom by square root of 29, I get 2 square roots of 29 over 29. And 5 square roots of 29 over 29. Again, I'm skipping over the rationalization work because you guys are really, really good at that. Alright, here's this I and j business. So unit vectors in the direction of the positive x and positive y-axis can be notated with, I'm covering up half my words, denoted by those two vectors there. And they're standard unit vectors. Again, I is not the complex number I. So there's a little note down there about watching out for that. Oh, and they also bold them in your textbook. So I bolded means this kind of I, the horizontal component of a unit vector. So this looks really complicated, but it's actually quite easy. So once you find your resulting vector, if it's a, where's that? Alright, so negative 2, 3, and 4, 5 are the initial vectors, is the initial vector the initial and terminal point. And then they found vector DE by doing our formula, and they simplified, of course. And then they denote it with I and J, just right there. And this is what it looks like to have, this has a linear combination, which is just fancy for like a linear equation or expression with variables. So, not too bad, right? This one's already done for you in your notes. So 2, 2, and 5, 4, they found the new resulting vector. Make sure you watch your order. It's always x2 minus x1. And then they just put I with the horizontal component and j with the vertical component. Ta-da! Alright, so same thing here on number 9. We need to find mj, or mn, hello, can't read, still can't read. Alright, x2 minus x1, negative 5 minus 2 is negative 7, and then y2 minus y1 is negative 11, and then they want the linear combination with I and j, so this is negative 7i, and then instead of plus negative 11j, can we just write minus 11j and call it a day? Like Dr. Seuss in here. Here we go. Number 10. Mn again. Keep rhyming. 18 minus 0 is 18. 4 minus 6 is negative 2. So in my linear combination would be 18i plus negative or minus 2j. Easy peasy, lemon squeezy. And then just to bring back some fun stuff. Your unit circle, you might want to have it out now. You can find component form if given a magnitude and a directional angle. Okay, we kind of already knew that because we worked with that in the last lesson, right? So you take the magnitude times the cosine, comma, magnitude times sine. These are all things we knew. But when you have special angles that are on your unit circle, you don't have to bother typing with the calculator because you know cosine of 120 is negative 1/2, and you know sine of 120 is square root of 3 over 2. So you can give me really pretty exact answers for your vector. Sometimes. Sometimes not. So 11, you're going to give me an exact answer because it's a unit circle number. And 12, not so much. So if you need to, you can draw this out. But my new vector, his components are going to be 18 times the cosine of 240, comma 18 times the sine of 240. My brain is just not in trig land right now, so I'm going to have to go look up cosine of 240, and it's negative 1/2. There we go. I would have eventually figured it out. And then sine must be negative square root of 3 over 2. So we're in the third quadrant. And then when I simplify, whatever I can simplify, like here, 18 over 2 is a 9. Same thing here. Yeah? Yeah. Yeah. So my, what do they want? My exact vector would be negative 9, comma, negative 9 squared root of 3. Lovely. This one, however, 95 is not part of my unit circle, so I just have to kind of deal with a not exact answer. So 5 times the cosine of 95, and then 5 times the sine of 95, and I'm just typing away on my calculator, which someone already did for me. I have negative 0.44, comma, 4.98. Lovely. Alright, well that was nice because we already knew that. It's in the coordinate plane, so nothing's really that crazy, right? It does say something about tangent, so remember, same tangent formula applies here as well. Tangent can be found by taking sine divided by cosine. So if you need tangent of an angle, you can take the components sine divided by cosine. Again, we did that because remember in our bearings question, when we used the component method, we had to find inverse tangent, but same idea, setting it up. Maybe I should have done this lesson first. Oh well. Alright, find the direction of each vector. Okay, so this next set, they're going to give us those weird little linear combination formulas for our vector. And you know me, I'm going to draw it out because this isn't very exciting to me. Alright, so this is the vector negative 4, 2. That's a little easier for me to think about. So negative 4, 2 would be like right here. So I know it's not technically appropriate to label a triangle negative, but whatever. Deal with it. And then what do they want? They want the directional angle. So if I could find that angle, I'd be in business. Now when I set up inverse tan of 2 over negative 4, which is totally fine, my calculator is going to give me the answer that it wants to give me, which is negative 26.6 degrees. So my calculator is giving me this angle down here. But remember, reference angles, in this case vertical angles, if this is 26.6 distance, this is also 26.6. So if they want the actual angle from the positive x-axis, and I need to find this angle right here, that would be 180 minus 26.6, which is totally 153.4 degrees. That's the angle they want. Okay, 14. Similarly, I'm going to draw it down here. To 17. Whoop. You know, I really should take like an art class or something because these are getting pretty bad. Alright, finding theta. This one's going to be nice and easy because my calculator is just going to go ahead and give me the angle I want. So inverse tan of 17 over 2, which comes out to 83.3 degrees, which is that exact angle. Well, it's not exact because I rounded, but you get the idea. Okay, that, my friends, is vectors in the coordinate plane. All right, best of luck.